All right, this is a pretty cool problem. So in this problem, we have a solid cylinder that's rolling across a table. The cylinder is attached by a cord. There's a yoke on the cylinder. The yoke's attached to the pulley that's running, or I'm sorry, an axle that's running right through the center of the cylinder. That's important because we need to know what the axis of rotation is for every object that's rotating, right? So we're told that it's a solid uniform cylinder rotating about an axis that's at its geometric center, basically. And that cord, massless inelastic cord, is running over a pulley. The pulley is a solid disc, mass M and radius R, and then there's a block that's suspended from the string. So proportionally, we're told that the suspended block, the hanging block there, has a mass M. We're told that the pulley has a radius, actually has a mass M and a radius R. And then we're told that the cylinder that's rolling across the table has a mass M and a radius 2R. So kind of an interesting problem. All the masses are the same. The radii are different here, but we get to kind of see how this ends up working out proportionally, which is neat. What we're asked here, and the M and R are given, right? We're asked to determine the speed of the hanging block after it has descended through some distance for R. And we're told that we can assume that the cylinder rolls without slipping and the system starts from rest. Okay, so this 4R, basically it's released from rest, and then 4R would be probably about this much-ish um, descending. And we want to know then how fast is the hanging block moving, right, after it's descended that much. So very, very well defined problem, but we've got these three moving pieces here that we need to keep track of. We're going to be considering this in terms of energy analysis here. So let's start off looking at that, remembering that our overall approach is change in mechanical energy is equal to the sum of works done by non-conservative forces here. Okay, so my initially, this whole situation is at rest. So I don't have translational kinetic, I don't have rotational kinetic. However, the hanging block is at its highest elevation initially. So that means that initially we do have gravitational potential energy for the hanging block. So I can express that as mg times the distance 4r, right? That's basically the elevation that it will travel through as it's traveling downward. So initially, all my energy is in the form of gravitational potential. And then finally, I'm going to give myself a little more space here. And by final, I mean after the hanging block has descended through the distance 4r, what's going on? And that is like everything's moving now, right? So we can go kind of one piece at a time. We can start with the block. The block itself is going to have kinetic energy, 1/2 mv squared. I'll just call that v. So that's the block. And then we can look at the cylinder. What's the cylinder going to be doing? Well, the cylinder is rolling across the table. So it's kind of a neat case in that it has both translational kinetic energy because its center of mass is in motion, and it has rotational kinetic energy because it's rotating around its axle. So we have to consider both of those. So the translational kinetic energy for the cylinder will be 1/2 m v squared. Notice this v is the same as the speed, the translational speed of the cylinder, the speed at which its center of mass is moving linearly across the table, is the same as the speed of the hanging mass because, again, they're attached by the string's inelastic. And now we need to consider the rotational energy of the cylinder because it's rotating as it's translating. So I'll call that 1/2 I sub 1 omega 1 squared. So just to keep track of things, right? This is the block. These two terms are for the cylinder. And then I have the pulley, right? The pulley is not translating, it's held in place, but it is rotating. So I have rotational kinetic energy here. I'm going to call the pulley moment of inertia I sub 2, and I'll call its angular speed omega 2 here squared. And so this here represents the energy of the pulley after the block has descended through some distance d. Okay, so that's taking everything into consideration here. Now we're told that the that the cylinder is a solid uniform cylinder here. So that means that I can figure out that I1 for the cylinder is going to be, I can look that up in the table, right? Look at the table of inertias and look up the different shapes. And that one is 1/2 mr squared. So 1/2 m. Now the radius here is 2r. You have to always make sure that when you look at the equations in the tables that you're popping in the values that are relevant to the shapes that you're using in your problem. I see a lot of students make errors by just like writing down the table equation and not applying the table equation to their problem. So this will give me here 2. By the time I square that, get the 4, divide by 2, that will give me 2mr squared for I sub 1. The pulley itself is a disk. So I sub 2, 1/2 mr squared. So 1/2 the mass of the pulley is m, the radius of the pulley is r. So that turned out pretty simple there. So this is, I know now I can sub in values for I1 and I2 just by using the table. Okay, now let's think about the right-hand side of our equation just a moment. How about works done by any non-conservative forces? So what are my non-conservative forces in this problem? I can think about what those might be. And are they internal? Are they external? So tension, definitely, right? You could say tension does work. Turns out the tension does positive work on the cylinder and it does negative work on the hanging mass, same amount there. So we're not going to consider tension here. Tension doesn't do any net work to the system as a whole. So our non-conservative works here, and we don't have any kinetic friction. You might wonder about the static friction of the rolling cylinder. Static friction doesn't do work in this case. And you will see a derivation for where I show that, like kind of explain like what's the relationship between static friction and work in the context of rolling, I should say. Static friction can do work in all kinds of other situations as we've seen, but in the context of rolling where you have perfect rolling like this, it turns out that the net work done by static friction is also 0. So the bottom line here is that the work done by non-conservative forces in this really very well-behaved case is 0. So that gives me an equation then that I can write for, I can just write my energy final is equal to my energy initial in this case, right? Since the work done by non-conservative forces is equal to 0. A couple other things that we should hash out here is just simply looking at the omegas. So we've got these two V's in the first two terms, but we have omega 1 and omega 2. So I would say pause and take a moment and figure out your omegas, right? So my omega 1 is going to be equal to, now which one is that? That's for the cylinder, right? So that's going to be equal to V over 2R, the radius of the cylinder. Whereas my omega 2, that's for the pulley, is going to be equal to V over R. So as you're going back and forth between omegas and V's, they relate by radius, but you always have to make sure that you're using the appropriate radius. So in this case, I use radius 2r when I'm talking about omega 1, which relates to the cylinder on the table, and I use r when I'm discussing omega 2, which relates to the pulley. Okay, so you can pop those in there. So for this omega 1 squared, we can substitute in there V over 2R squared, quantity squared, and omega 2 V over R squared. Substituting those for omegas and I's, and I'm going to actually do another step here. So let's write that out. Energy, setting energy initial and energy final equal to each other. So the energy final equation, I'll just kind of box these little guys over here. Energy final equation is going to be 1/2 big M V squared for the block plus 1/2 big M V squared for the cylinder plus 1/2. Now here's I1, right? I'm still on the cylinder. I1 is 2mr squared, and then omega 1 squared, right? So V squared over 4r squared. Okay, sometimes I like to just do the squares right away rather than keeping it external because I'm always worried I'm going to forget to square that too. That's in the denominator. So 1/2 I1 omega 1 squared plus 1/2. Now I2, we figured out that was 1/2 mr squared times omega 2 squared. So that's going to be V squared over r squared. And that'll be equal to 4mg r. All right, we can simplify that a little bit more, of course. 1/2 and 1/2 mv squared is just going to be mv squared. And then we can figure out these terms here. 1/4 1/2 2, so that'll be just my 1/4 m v squared plus, and again I have 1/4 mv squared there is equal to 4mgr, and this simplifies even more. You see that on the left hand side now I have 3/2 mv squared is equal to 4mgr, and then we can solve for v here. And we'll end up with root 8gr over 3 for the speed. So that's my final result.